Hey guys, I'm just going to be going through one of the questions. This is one of the questions from our quiz. Reads like this. Consider a T-shaped column with a knee welded on the face. A load is applied at the end of the knee as shown. Calculate the induced stresses in the column at P and Q. So the procedure for this question has 5 steps. Our first step is to find the centroid of the section. The second step is to find the area moment of inertia around the centroid or around the neutral axis. Our third step is to find the equivalent loads being applied to this section. What that means is we've got this load of 600 newtons being applied on the knee. I need to determine the amount of bending moment and load being applied at this section at AA. So for that, we'll be able to use that to find out the forces at P and Q, which are missing from our diagram. So P is at a location here, and Q is at a location here. Okay. So once we find out our area moment of inertia for this shape, we will use this to determine or approximate the stress due to bending at points P and at point Q. And we'll also need information about the cross-sectional area to find the stress due to this direct load being applied on our section. So let's get started. Our first step is to find the centroid. There's 2 ways we can find the centroid. Both of them use the same formula. I'll use the formulaic method for this. So just to determine the centroid, we use a formula. In this case, x bar equals the sum of the area of each of our shapes, the centroid for each of our shapes, divided by the sum of the area for each of our shapes. So this is the cross section that we're dealing with at the moment. So I'll redraw this just over here. I will call this my first section, and this my second section. And I can pick a datum, a reference point, and this reference will be where my center of area is measured from. So my reference I will pick in this case will be from the right hand side. So I will need to determine the center of area for each of my shapes from this position here. So now I've separated my section into 2 sections, 2 shapes. I can mark where the center of area is for each shape. So for the first shape, it's in the middle here. For the second shape, it's in the middle here. And I can determine the distance to travel to this position here from that axis. I can determine it from here. So the distance to the centroid of this first shape from that axis will be my value of 10 millimeters here divided by 2, so it's halfway of this distance here. So my first value, so that's the distance I want, and my value of x bar 2 is equal to 0.005 millimeters. My value of x bar 1, which is my distance to the centroid of my first shape, is that distance there, and I can determine it just from the dimensions that are provided. So it will be halfway on this shape here. This distance here is 10 millimeters. I know that this distance here is 10 millimeters, that distance there. So I can then determine that the distance to get to here from this reference will be 10 millimeters plus 10 millimeters. So x1 will be equal to 0.2 millimeters. I can determine the area for each of my shapes. So the area of the first shape is just 15 millimeters times 20 millimeters. So just 15 millimeters times 20. And I can determine my area for my second shape, A2, and that will be 10 millimeters times 25 millimeters. Right, so 10 millimeters times 25 millimeters. So those values will be so for the first shape will be 0.0003, and that's meters squared. Sorry, this is in meters, and that should be in meters. And my second shape will be 0.00025 meters. I could have kept all of this in millimeters and I would get a result in millimeters. At this stage I want to get a result in meters. Okay, so now I can just substitute these values into the equation. So this equation here expands into this. I can write this value out. So this expands into area 1 times x bar 1 plus area 2 times x bar 2 divided by the sum of my areas. So area 1 plus area 2. So I can just take each of these values that I've determined from that diagram to determine my centroid. So A1 is 0.0003. X1 is equal to 0.02 plus A2. A2 is 0.00025. So that's in meters squared. And x2, we get it from here, 0.005. Can't see that, sorry. 0.005. And then that's all divided by the sum of the areas. So 0.0003 plus 0.00025. To repeat again, you could probably do all this all in millimeters and you'd avoid having to write all of these 0.00s and you get an answer in millimeters. Okay, so putting this into a calculator, we get our value for x bar, and in this case I get my value of x bar equal to 0.0138 meters. So what this means that the distance from here to the center of mass of my shape is 13.82 millimeters, or 0.01382 meters. So there is my centroid of my shape. Okay, so I'll just write this down here. So x bar is equal to 13.82 millimeters. Okay. Our next step now is to determine the area moment of inertia of our shape around the natural axis, the neutral axis. So what we've been spending our time now determining is the location of the center of area. And our neutral axis coincides with the center of area. So I can draw my shape. And I can draw my neutral axis. Located at 13.82 millimeters from that position. Now, so the strategy that we're going to use to determine the area moment of inertia is to determine the area moment of inertia of each of our shapes around its centroid. And then we will use the parallel axis theorem to shift the value from our centroid to the neutral axis. So I'll call this value, so I called that shape I called this shape number 1. So I called that distance moved here h1, and I call this distance here from the centroid to my neutral axis h2. So that's the distance to shift from there to there. So I can determine that distance. The distance I can determine that from, well, I know the distance here between the center of shape 1 and this reference point here. That's equal to 5 millimeters. I know that this distance here is 13.82 millimeters. So from that, I can determine the distance h2 by going 13.82 millimeters minus 5 millimeters. So h2 is equal to 13.82 millimeters minus 5 millimeters. So h2 is now equal to 8.182. I can also determine this distance here, the distance h1. The way that I can determine that is the location of this center of area for shape number 2 is, well, from here to here it will be 20 millimeters. So 10 millimeters here plus 10 millimeters here, that gives me 20. And then I know this distance here is 13.82, so it will be 20 millimeters minus 13.82 millimeters. So h1 is equal to 20 millimeters minus 13.82. So the value I get is 6.812 millimeters. Oops, 6.818. Brilliant. Okay. So now I can determine the area moment of inertia for the shape around its neutral axis. And what that will be is the area moment of inertia for my first shape around the neutral axis, plus the area moment of inertia for my second shape around the neutral axis. So what I'll do is I'll find the area moment of inertia of that shape. So that will be my area moment of inertia, I would say moment of inertia from now on, for the shape around the neutral axis will be equal to the moment of inertia for the first shape around the neutral axis plus the area moment of inertia of the second shape around the neutral axis. The area moment of inertia for the first shape will be equal to the area moment of inertia around its centroid. So the base will be 1 over 12 BD cubed. So B is 0.015. The depth, or D, will be 0.02 cubed, and it's over 12. I'll use a parallel axis theorem now to shift the area moment of inertia from here to the neutral axis. My distance h1 is equal to 6.818 millimeters. So here I'll go plus AH squared, so the area of my shape is 15 millimeters plus 20 millimeters. So 0.015 times 0.02 times h squared, so times this value squared, times 0.68, whoops. So I started writing it in the wrong value, 0.0068 squared. And then now, so that's my value of I1 around the neutral axis. I'll also now add I2 around the neutral axis. So I2 will be the base, 1 over 12, so plus 1 over 12 times the base, which will be 0.025 times this value here, which is 10 millimeters, 0.01 cubed, plus the area of my section, so 0.01 times this distance here, 0.025 times this value h, so the distance that I'm moving that section to get it to the neutral axis. So h2 is 8.182 millimeters. So times 0.008182, and that value is squared. So you probably can't see it. There you go. That value is squared. So when I evaluate this equation, I get I equal to 42.77 times 10 to the negative 9 meters to the 4. So this is the next value that I've required, and this is actually what I needed my x bar for. I'll also need it for my moment as well. So I'll write this value up here. I around the neutral axis is equal to 42.77 times 10 to the negative 9 meters to the 4. Alright. Okay, so now that I've got my eye around the neutral axis, I can try to determine the stress at, actually no, first before I do that, I'll determine the forces acting on my cross section. So here's a picture of my cross section again in a 3D view. Alright, here we go. And I will be determining the forces that are acting on this system. So this force, I will replace it with a force acting on the neutral axis. So here's my neutral axis. And I'll also replace it with a bending moment. A bending moment that goes this. So here's my force, and here's my bending moment. The value of my force will be equal to this 600 Newton value here. So because this force is offset, it will also try to bend my material as well. So you can kind of picture, here's my beam, there's a section hanging off the side of it. That force is trying to bend the attachment here, so then the whole shape tries to bend that way. Okay. So my value of F, I can take straight from here. My value of M, I determine, M is determined from the force times the distance. The distance that I use is the distance from the neutral axis. So that distance there to the neutral axis was 13.82 millimeters. So my total moment will be M equal to the 600 Newton force times the distance of 75 millimeters plus 13.82 millimeters. So 75 millimeters plus 13.82 millimeters. Okay. So now from this, I get my moment. My bending moment will be 52.9 Newton meters. Awesome. Now, so I've got my area moment of inertia, my force applied to my system, my moment being applied to the system. This is most of the information that we require in order to determine the stress at points P and Q. So the stress at point P will be equal to the stress contributed by axial, by my axial load, plus the stress contributed due to my bending load. My stress due to my axial load is equal to force divided by area. My stress due to my bending load is equal to my bending moment times the distance to the point that I'm interested in. So for P, it's this distance here. I call that my Y value, my Y, divided by the area moment of inertia around the neutral axis. Okay. So if I know area we've calculated previously, M we know as well. My value of Y will be this distance here, so it will be 30 millimeters minus 13.82. And my value of I know from this equation here. Okay. This force F is trying to compress the whole system, so it will be a negative force. This force M is trying to, it was trying to bend it in this direction here, so it's trying to create tension at point P, so this will be a positive value. Okay, so force is 600 newtons. Cross-sectional area is 0.00055. So that's just calculated by finding the area of that shape and adding it to the area of this shape. My moment is 52.9 Newton meters. My distance from here to here is going to be around about, well, I'll just put it into the calculator. So 30 minus 13.82, so around about 16 millimeters, so 0.01618. Divided by I, which we've calculated up here, 42.77 times 10 to the negative 9. And now I can calculate what my stress at P is equal to. So stress at P will be equal to 19.35, and the units for this will be megapascal. Okay, cool. I can also determine the value for the stress at Q. So my stress at Q will be equal to my stress due to axial load plus my stress due to bending. At Q, the bending moment is going to be in compression both because of the direct axial load and also because of the bending. So if you imagine that the system is made out of rubber, this bending is trying to compress on that side, on the Q side, and it's also because of the bending part and also because of this compressive load of 600 Newton. So this value of M is going to be negative, so there will be a negative that's introduced. My compressive load here, sorry, that was supposed to be a negative. My compressive load here, so this will be negative. And actually, let's go through this part. So Q, I'll get negative 600 newtons divided by my area. So the area is the cross-sectional area is the same. Cross-sectional area is 0.00055 minus the bending moment applied, so 52.9 Newton meters. Again, it's off for now. So of course I'm using SI units for all of this. Y is going to be my distance from here to point Q. The last time to get to P I used this distance, to get to Q now I'll use that distance. So this is just going to be this is going to be my 13.82 millimeters, or 0.01382. 0.01382 divided by I already got 42.77 times 10 to the negative 9. I can evaluate this this equation, and I will get for Q equal to minus 17.76 megapascal. Awesome. Okay, this is the end of this question. So our final solution is stress at P equal to 19.32 megapascals, and that's in tension. And my stress at Q is negative 17.76. This indicates that it's in compression. Awesome. Thanks for listening to my first video. Goodbye. See ya.